The glass in this problem is to be coated with a thin film with a thickness of T so that reflections are eliminated at a wavelength of 600 nanometers. The reflected wave shown here is eliminated by destructive interference from the wave returning from the reflection off the glass. Before we can write the condition for destructive interference, we need to count the number of phase shifts. There's one at the first surface, where the wave reflects off of the air-film interface, and there's another one where the wave reflects off the film-glass interface. In both of those cases, the second medium has a higher index of refraction than the first, so they both have a phase shift. When we have an even number of phase shifts, destructive interference occurs where twice the thickness of the film equals m plus a half times the wavelength in the medium, where m is an integer from 0 on up. The wavelength in the medium is the vacuum wavelength, lambda naught, divided by the index in the film. And we can solve this equation for the minimum thickness by realizing that T min, the minimum thickness, occurs where m equals 0. In solving for T min, to see that it equals the vacuum wavelength divided by 4 times the index in the film. Substituting values and calculating gives us 120 nanometers for the minimum thickness of the anti-reflection thin film coating.